For this example, we have that the half-life of the radioactive element plutonium-239 is 25,000 years. If 16 grams of plutonium-239 are initially present, we want to find out how many grams will be present after 30,000 years. So the two most common applications of things with half-life, things with exponential decay in this way, are talking about carbon dating, where we want to see how old something is in terms of the amount of carbon left in it, where this is really only used for things that are properly ancient because carbon does not have a particularly short half-life. And then the other thing we use this for is finding out how much of a radioactive isotope we can expect to be left after a certain amount of time at a place like, say, Chernobyl.
What does the decimeter say?
3.6 Roentgen, but that's as high as the meter.
3.6. Not great, not terrible.
Where in this case, we're not actually given a whole lot about our model, so we have to be a little bit clever about how we set things up. We want to eventually get something into that form, but we're not really given much. We aren't told implicitly a whole lot with what t is. We know nothing about k, and we're given a0, but a0 is not entirely helpful by itself. What we can do instead is recognize that in terms of the half-life, we have an amount a that is equal to any initial amount, regardless of what it is, in this case 16 grams, but it really doesn't matter, over 2, because that's half of it, will occur for any value a0 times e to the 25,000 t, because the half-life, 25,000 k, I keep getting my k's and t's backwards. But in any case, this will happen because our half-life is 25,000 years, so we will have half of whatever we started with, regardless of what we started with at that point. Which means that we can divide out those a0s, and for any amount of plutonium-239, we have that 1/2 is going to be equal to e to the 25,000 k, not 25,000 t. I don't know why I keep doing that, but whatever. That's what we have here. And then solving this is actually very straightforward. We just take natural log of both sides, divide out 25,000, and we'll get that k is equal to the natural log of 1/2 over 25,000, where I'll say the natural log of 1/2 is not a particularly nice value, but it is one that comes up a lot. So it's one that might be worth knowing. For one reason, you can think of that, is this is actually just 2 to the negative 1. Pull out the negative 1, so it's negative natural log of 2, and natural log of 2 is another one that comes up a lot. So just, you'll get used to seeing those. But anyway, in this case, we want something nice to represent k there, so you don't have to plug in something like this every time we need a value. Here, we can approximate k as negative 0.00003. So it is a negative number, but it's a very, very small negative number, which should seem reasonable, because the half-life's 25,000 years. That's a really long time. So this should decay very, very slowly. And then if we want to get the amount that we would have after 30,000 years, so we'd have t equals 30k, we just plug in our values. We want the amount a, where a0 here we're starting with is 16 grams, e is still e, and we're going to take 30,000 multiplied by negative 0.00003. I don't know why I wrote those backwards, but that's okay. And this is our most exact answer, but it's not really a nice number of grams, so we will round this off to say that it is about 6.51 grams of plutonium-239, which should make sense, right? This isn't exactly a linear change, but that is 5,000 more years than the half-life, so it should be a little bit less than half. And in this case, 1.5 out of 8, well, that's about 15–16%. It's about 1/6. And 5,000 is about 1/5 there. So it's not quite perfect, but it should at least be a reasonable value. It should make some sense if you understand what it is that we're actually modeling here, where these ideas are nice for certain things that have very consistent behavior, but There are a lot of other models that seem like they should be exponential until they run into a very natural and predictable capacity. And that's where we get into an idea called a logistic growth model, and that's what we'll see next.